Good evening to the very last joint astronomical colloquium of the summer term 2017. It is a great pleasure to welcome John Magorrian from the University of Oxford, who will talk about the center, not of our galaxy, but of the big neighboring galaxy of M31. Let me introduce the speaker. John got his degree in the Queen's University in Belfast. Then he moved over the channel, separating Ireland from Britain, to Oxford to get his PhD there. From that, he even crossed a bigger channel. He moved across the Atlantic to the Canadian Institute for Theoretical Astrophysics. After that, he came back to Cambridge and got a Royal Society University Research Fellowship, which brought him then to Durham. And since a long time, I think, he is now in Oxford, back in Oxford to where he got his PhD. And as you all know, he's very famous for the Magorrian relation relating the masses of black holes to properties of the galaxies, to the bulge. And he will talk about the specific case of this relation. He will talk about the center of M51. So please let's welcome John.
Thank you for your patience. Thank you for coming out in the rain. I'm going to talk to you about, as Raz says, the center of the M31 galaxy. But before I do that, I'll give you a brief overview of why this topic, I think, is interesting. Right? And suppose now, if we introduced ourselves to an alien, say a condensed matter physicist, and we asked the alien to describe what do we do, I think a fair description of probably about what half of us do is that we study the structure, formation, and evolution of self-gravitating blobs of matter, right? Okay, that's, I think, a fair description of roughly what half of us do. Okay, and when you look at our successes in this area, well, the condensed matter physicists might look at, say, scales of 10 to the 30 kilograms, in other words, stellar scales, and say, yes, we're doing very, very well. We basically understand the structure and evolution of stars, at least in the broad details, compared to everything else. We don't necessarily understand how they form, but stellar structure is pretty mature. Okay. If you move up on scale to, say, scales of globular clusters, then it becomes a bit more sterile in many ways, but at least dynamically, we understand the broad features of how they work. At least we think we do. We haven't asked the right questions to really probe our understanding of them. And then you move up in scale again to 10 to the 40 kilograms and above, galaxy scales. The answer is, we don't really have a clue what's going on. We've got some hints of what's going on inside galaxies, the formulation, but by and large, there's still a mystery. So here's a list of various things that we don't know about galaxies, and throughout this, I'm going to ignore gas. Throughout my talk, I'm going to ignore gas because it's too hard, and I've got graduate students to do that for me. So, first question is, how is matter distributed within galaxies, right? In particular, how is dark matter distributed within galaxies? That's not clear. We've got a pretty good idea of how the stars are distributed in projection, but the dark matter is a mystery. The other interesting thing about dark matter and stars is you don't really care just about their density distribution in three-dimensional space. You care about their density distribution in six-dimensional phase space, right? An important difference between galaxies and stars from the point of view of a condensed matter physicist is that the particles, in other words the atoms in a star, have very short mean-free paths, so they get randomized very quickly, whereas the particles, in other words stars in galaxies, they get extremely long mean-free paths. So you'd hope then that this phase-space distribution function in galaxies will tell you something about how the galaxy formed. That's why it's interesting to figure out what it is. And of course, whenever it comes to stars, there are actually different types of stars with different ages, different metallicities, and if you can probe the distribution function as a function of age, metallicity, and phase-space coordinates, then we learn even more about how the galaxy formed. Okay, but of course we don't actually know any of this. Okay, so here's two ways to investigate galaxies. Just close this door. Two broad ways. One is to look at populations. So in this case, you look at the gross properties of galaxies, such as Tully-Fisher relation, fundamental plane, and this red cloud, green valley nonsense that's become very popular recently. And this is kind of akin to the Hertzsprung-Russell diagram for stars. Kind of, vaguely. The alternative extreme is that you drill down and you dissect galaxies one by one. Right? So in other words, you do some kind of chemodynamical modeling. And that's the approach that's really taken off now with the launch of Gaia and associated surveys. Right? That's applied to the Milky Way. In other nearby galaxies, we have to rely on integrated starlight, so we can't do such a good job there, but we can still say something interesting. And that's kind of akin to stellar structure modeling, or if you want to be really fancy, helioseismology. Right? So today, I'm going to focus mostly on the second method, on drilling down. I'm going to dissect the very bottom of the potential well of just one particular galaxy. But before I do that, I want to give you a reminder of what the population studies of galaxies tell us about the bottoms of these potential wells. Okay, first fact, Ralph mentioned it, is that at the very bottom of most potential, these big potential galaxy potential wells, you find a big black hole at the center, right? The mass of this black hole correlates with the mass of the surrounding bulge properties. So for instance, it's roughly 0.2% of the mass of the surrounding stellar bulge. Or an alternative way of looking at it is that it correlates with the velocity dispersion of the associated bulge, which is understood to be a better measure to the Weyl theorem of the depth of the galaxy's potential well. Right? That's the first property. That was discovered about 20 years ago. It was widely accepted about 20 years ago. Then about 10 years ago, it became accepted that nuclear stellar clusters are a thing in most galaxies. So they're very obvious whenever you look at very late type spiral galaxies, right? Because you get these clusters of young stars, and in late type spirals, they're the closest you get to a galactic bulge. Right? But if you look very closely at various other types of galaxies, you find that there are young stellar populations at the very centers of at least a half of the early and late type spirals, dwarf ellipticals, and the lower luminosity ellipticals. So not the big guys like M87, but the more standard boring ellipticals like NGC 3115 and that's just a day zero, 3379, and I could rattle off more telephone numbers. Okay. Now the funny feature about these is that they all tend to have bursty star formation detectable within the last 10 to 8 years or so. Okay. So this opens then three questions. First one, most obvious one, is how do the black hole and the surrounding stellar bulge know about one another, right? You've got this correlation between these two quantities, and they've got very different characteristic sizes. So for instance, the bulge characteristic radius is of order kiloparsecs, whereas the so-called sphere of influence of the black hole is of order parsecs in size. So the question is, how do these two know about one another? Right. Next thing is, what's the connection between black holes and nuclear stellar clusters? When presumably you find these two objects at the centers of galaxies, they both have their own individual scaling relations. How are the two connected? That's not clear. And then the third question is the one that interests me the most, is that you've got these galaxy centers, the densest stellar systems known in the universe, where the density goes up to 1 million solar masses per cubic parsec. And the question is, what kind of interesting dynamical processes are going on there? So for instance, you've got collisions of stars, you've got possible tidal disruptions of stars by the black hole, you've got gravitational radiation that is caused by compact stellar objects falling into the potential of the black hole. So you'd like to understand what do these effects look like, how often do they happen, should we be planning to go out and observe them and then learn more about general relativity? Okay. So the solution to all of these, I argue, is to drill down and look at nearby galaxies. The best one to study is our own Milky Way, but I'm going to instead today talk about our nearest big neighbor, the Andromeda Galaxy. Okay. And there's a picture of it. I'm sure you've seen it, maybe not in quite so much detail, but it's a familiar, kind of boring-ish, early type spiral galaxy. And for me, the interesting thing about it is whenever you look at the center, it has a double nucleus. Right? So here, you see it's got two bright peaks. This is on arc-second scales. Okay. So this is an outline of my talk. This is for you to decide when you want to go to sleep. Right. First, I'm going to begin by giving you an overview of the central regions of M31. Then I'm going to go over Tremaine's very clean and elegant explanation for this double nucleus. He explains it as an eccentric disk orbiting a black hole. And of course, he came up with this before it was widely appreciated that most galaxies had black holes in the center. And then I'm going to talk about various applications of Tremaine's picture applied to this. So I'm going to start with the simplest possible models, which of course assume only Keplerian physics, just basically Kepler's laws of motion, Keplerian orbital elements. I'm going to provide a model that gives a wonderful fit to the data. And then Mr. Newton is going to come along and throw a couple of spanners in the works and saying, no, your model's not very good. But then two Germans come to the rescue, Gauss and Schwarzschild, and they say that, that's okay, all is probably okay with their models, but we're not totally sure. Okay, and then I'll end with some implications of the models that we find. So I should point out that the person that did most of the work in this was my graduate student, Callum Brown. And he's about to do his thesis defense in just over 2 weeks. So you have to ask me lots of nasty questions at the end so I cannot tell him what they are. Okay, so here's a bit of the bigger picture of M31. First thing is its distance is 800 kiloparsecs away. And just give you the idea of scale, that means that 1 arc second at that distance corresponds to roughly 4 parsecs. This shows the J-band light of the galaxy on very, very large scales. And you see when you plot isocontours of it, it has this kind of weird boxy shape in the middle. Then it's got these disky isofolds, and it looks like there's a tilted bar. Right? And this has been modeled successfully by a number of people, and they find that they can reproduce most of these features. And for our purposes, the one thing we want to remember about this is that their models suggest that the disk in M31 is inclined to us by an angle of about 77 degrees. Right? That's the one thing I want you to remember about this slide, is that the main body of the disk is inclined at 77 degrees, according to these models. So 77 degrees. Okay. Now let's look at the nucleus. This shows with pick 2, or probably even with pick 1, observations of the central few arc seconds taken from Laura et al. You see that there are 2 bright spots. Right? The brightest spot is not surprisingly called P1. The faint spot is called P2. And if you squint very carefully, you see P2 is actually slightly blue. So let's call that P3. Right. This is then what it looks like. This is the V-band image with the basically color-coded according to V-band intensity. Okay. You see the double nucleus stands out even more clearly in this kind of plot. Right. There's P1, P2. The highest resolution observations of the highest resolution spectroscopic observations of this have been obtained by Bender et al. 2005 using the STIS instrument on HST. So they placed a long slit in STIS sort of that it intersected, crossed both nuclei, and they measured the stellar kinematics across that direction. And this is what they look like. This shows radius as in arc seconds. That's the mean streaming velocity of the stars.
That's the velocity dispersion of the stars, and then these two measure the shape of the distribution of line of sight velocities. First, two things to note are, first of all, is that the velocity profile is actually very asymmetric. Right? There's fairly big peak-to-peak swing in velocity. It goes from minus 300 and something up to plus 200 and something, with a very steep gradient across the center. It's asymmetric. And the velocity dispersion is even stranger because it doesn't peak at the photometric peak of the galaxy. Instead, it peaks at the position of P2, secondary. And in case you're confused by this, actually these axes are swapped in the wrong direction compared to the previous plot. Okay, so here's some characteristic numbers for this system. Right. You've got a distinct nucleus at the center of this galaxy, which has a luminosity of around about 6 million times that of the Sun. Right. It's got two separate peaks, P1 and P2. These two peaks, as far as we can tell, they have identical colors. They're both old red stellar populations. And the only kind of interesting wrinkle about them is at the center of P2 is that there's this frosting of blue stars. Right. This P2 also happens to be the photometric center of the galaxy. If you look at the large-scale structure of the galaxy, P2 is to within 0.1 arcseconds the center. Right. The separation between the two peaks is about 2 parsecs in real units. And the velocity separation is roughly 200 kilometers a second. That gives you a characteristic dynamical time, if you do it in your head, of around about 10 to the 4 years. So it's pretty short by our standards. Okay, so there are a number of explanations people have proposed for this. One is that it's two distinct clusters. Right? Well, the problem with that explanation is, well, how do you get two clusters that have almost identical stellar properties? And as far as we can tell, they've got identical stellar properties. And if you had two such clusters, you'd expect them to spiral into one another very quickly. In fact, the dynamical friction timescale for these two clusters would be about 10 to 8 years, which is slightly short, comfortably short. Another possible explanation is that there is a dust band running through a more complicated nucleus, but again, there's no evidence of any differences in colors in between there, so that's ruled out. So it's a bit of a puzzle, and then, well, actually, before a lot of these observations were obtained, Tremaine, 95, came up with his eccentric disk picture, and it's extremely simple. It says this double nucleus is just a projection effect. Right? What you really have is a black hole and a cluster of stars going around it on an eccentric orbit. And then when you look at that in the right way, or if it's oriented the right way, you see two bright spots. Right? Okay, so there have been subsequent dynamical modeling of this by a number of people. Actually, not that many, I think, given the interest in this. So Stapler led the way with 2D models, then Bacon et al. Did 3D models, did n-body models, and they also got some further observations. Salvatore n-body, Paris and Tremaine, orbit superposition, Benner et al. Sort of virial models, and some ab initio simulation work, including some by people here in Heidelberg. Okay. So I want to go back to Tremaine's original model and then build on that, starting with various levels of sophistication in the dynamics. Right. Okay, so here's Mr. Kepler. Right. We just have a black hole and stars orbiting around it. Okay, so we forget all about stellar mass, we forget all about general relativity, and we just have a Newtonian point mass. Right? Then, if you remember your first year classical mechanics, all orbits in that potential, they're just simple ellipses, right? And you can characterize them by 5 numbers, right, which are constant. They're all constant in time. So you need 2 numbers to describe the size and shape of the ellipse, semi-major eccentricity. And then you need 3 angles to specify the orientation of the ellipse. Yeah. Right. And so because then, if you remember another thing about elliptical motion, stars linger at apocenter, right? And that's what gives you the bright spot at apocenter. So here is a clump of stars, right, with a range of semi-major X's and a range of eccentricities projected along the z direction, right? So whenever I talk about this, I'm going to talk about a disk. It's going to have x-axis is going to be the long axis, y-axis is going to be intermediate axis, and the z-axis is going to be the short axis. So this shows top-down view of the xy distribution of this clump of stars. You see, you get a bright spot out here where stars linger. Since I like Euler, I can introduce 3 more angles. Right? And I can orient these disk axes on the sky. Right? I can just turn this around. So I get the 3 more Euler angles, and I can view this disk edge on. And you see then that I get a bright spot close to where the black hole is. Right? If I look at it at intermediate axes, there, you get 2 peaks. Right? And this essentially is the essence of Tremane's 95 eccentric disk model for this. It's just that you happen to see an eccentric disk which in projection gives you these 2 bright spots. So there are various, this doesn't look particularly much like what we actually observe in M31. And so there have been a number of efforts taken to try to describe that. And what I'm going to talk about next is the first paper done by Callum, my graduate student, in trying to make a detailed model of this by using the Kepler assumption. And this is really a follow-up to Pyrus and Tremaine, who had what I think is the best models before Callum, the models that give the best description of the observed kinematics before Callum's work. And they came up with a very, I think, inspired choice of distribution function for the orbits in this, which we didn't really understand. So we thought we would take the distribution of orbits, so we took the basic idea that they used, right? In particular, we kept the assumption of reflection symmetry in the y and z planes in their eccentric disk model, and we decided to be maximally clueless. Right? We said, we don't really understand what this disk should look like, except that it's going to be a sum of some blobs in these orbital elements, right? So we're going to assume the orbit distribution is just given by a weighted sum of a number of blobs. So each blob here is just a normal distribution in semi-major axis times a normal distribution in eccentricity times some kind of normal distribution in the z direction. Right? That's all that this is. It looks complicated, but it's just a blob in orbital weight space. Okay. And we take fixed knots in semi-major axis, eccentricity, and the spread of the inclination angles, and that leaves us then with just a few free parameters. Well, not a few, these would be 800 free parameters, but they're not all interesting. So the first free parameter, most important one, of course, is the black hole mass. The next one is what is the orientation, the 3 Euler angles of this disk in the plane of the sky. And then finally, what are these weights? So how much of each of these blobs in A, E, and I do we have to include to match the observations? Okay. So the nice thing with this model is you can, for each one of these blobs, you can calculate what it looks like in projection. You can calculate the effect that it has in the kinematics. It's all pretty straightforward. It's just lots and lots of integration. And then we can infer the distribution of orbit weights by essentially fitting these blobs to the available observations. Right. And this is what you get. This shows the fit to the photometry. And you might not be surprised to know that given that we have got 814 free parameters, we do get a pretty good fit. Right. But I mean, I think it's harder to get a better fit than that. Right? We're fitting the surface brightness fluctuations in this model, more or less. But, yeah. Okay. What comes next? Here, next up then is the velocity distribution. Right? This shows the fit we get to this velocity distribution along this slit for different values of black hole mass. Right? You see, the black model here is our favored one. It has a mass of around about 10 to the 8 solar masses, right? But we can vary that mass by at least 20%, and we get results that are pretty much, they're not really all that much different. Chi by I isn't different. And the one thing that we're always going to fail to fit is this kind of weird dip here. That's one thing we can't fit. Okay. The velocity dispersion profile, again, it fits very nicely. You could argue it's a bit too high in the very center, but we can think of ways of depressing that. Similarly, the shape of the deviations from Gaussianity, we can fit very well. It's amazing. Right, and even better, our models made a prediction, well, a post hoc prediction. So Bacon et al., they measured the kinematics of M31 using the Oasis integral field unit. Right? So instead of getting just a simple slit, they can actually map out the distribution of line of sight velocities across the face of the nucleus. That's what's plotted here in the color map. And the contours show what our model predicted for this. And you see that it agrees actually very, very well. And here's the velocity distribution. Sorry, the velocity dispersion distribution. Again, it agrees very well. This is what the disk looks like when you look at it on the plane of the sky in good detail. If you look at it edge on, it looks like that. If you look at it face on, it looks like that. Of course, actually, it's really surprised that we found it. Right? It looks. Whenever I find this, I go, what? It's a bit surprising. But unfortunately, it's actually degenerate. So I can make this cycloptic and even happier just by, we've got a lot of variation in the possible solution we have to this, right? But essentially, it always has a big, happy, smiley mouth, although sometimes you look more surprised than smiling. Okay, so that's the Kepler models. They have the benefit of being really, really simple, easy to run, but unfortunately, they don't really tell you very much about dynamics, right? It's just going back to 17th century physics. So let's introduce some. This is still 17th century, but actually it's a lot of years, about 50 years after Mr. Kepler. So whenever we include Newtonian two-body interactions, then we get a small problem, two small problems. The first one is this. I was very excited when I discovered this. Here is what the distribution function of our best fit model looks like. This shows the semi-major axis as a function of eccentricity, right? It's very similar to the earlier models of Paris and Tremaine. Just some of the details of how eccentricity various function radius differ, and we also find that there's an anti-aligned set of orbits on larger radii. That's not particularly interesting. The interesting thing for me was the velocity dispersions in different directions in the disk. So in particular, when you look at the velocity dispersion, the dispersion in inclination versus the dispersion in eccentricity, right? And we did this calculation of what those were for our best fit model. We found a ratio of 2 to 1. Right? Yes, of course, that's what people know. That dispersion has to be for a two-body disk, right? So there's classic papers by, say, Ida, Kokobu, and Makino, who look at two-body relaxation in axisymmetric, say, protoplanetary disks. And they find this ratio, sigma I to sigma E is a half. If you look in the solar neighborhoods, if you look at the velocity dispersions of stars, sigma Z to sigma R is also half for more or less exactly the same reason. And I was excited by that, but then I looked more closely, and unfortunately, it's the wrong way around, right? These guys predict it should be a half. We're finding it's 2, right? Right, that's one loose end. The other loose end is that our potential isn't really Keplerian, right? So we have a center Kepler point mass, and we find a black hole mass of 10 to the 8 solar masses. Yep. But then look at the luminosity of this nucleus, right? It's 6 by 10 to the 6 solar, right? So if you take a reasonable value of the mass to light ratio of this old stellar population, then you're going to get that the disk mass is at least 1/10 of the mass of the black hole. So it's a pretty strong perturbation on it, right? So this Keplerian this Keplerian approximation is only really a 0th order approximation. Of course, this was anticipated by Tremaine in his original eccentric disk paper, and he pointed out that a massive disk will cause orbits to precess at different rates, and so some mechanism is needed in order to keep the line of upsides, basically the pericenters, all lined up and stop them from precessing. And this mixing up into a boring axisymmetric disk. Okay. So in the rest of this talk, what I'm going to assume is that suppose that this black hole plus disk system is stationary in some frame. Right? So if you look at this, some frame that's co-rotating about this disk, suppose that there exists such a frame in which this is stationary. Well, first question is, does such an equilibrium actually exist? What's the pattern speed? And what does this perturbation do to the stellar orbits? Okay. So Gauss comes to our aid here in explaining at least the first loose end. Okay. So here is the point is that if you add a weak perturbation due to the disk on top of your black hole, then you find that that makes the orbital elements of the stars change very slowly. Right, so if your perturbation is weak enough, the time scale for the change of the orbital elements will be much longer than the actual orbital period. Right? And so you can go back to Gauss's 1818 paper, and you can calculate the change in these two vectors, the angular momentum vector and the eccentricity vector, just by averaging the stellar potential over the orbit of one star. Right? That's just, so in other words, essentially you replace the stars by rings. Yeah? And you find here, this shows what you get when you do this calculation for blobs like this, but of different eccentricities. Right? You find that whenever the eccentricity is 0, if you get circular blobs, then they've got retrograde precession. That shows what this delta omega here is the precession rate of the line of nodes. And as you increase the eccentricity, that becomes slower and slower and slower until about an eccentricity of 0.5, it actually becomes prograde. Right? So the whole system starts to rotate, precess in the same sense as it goes. Then if you look at the dispersion in the eccentricity as a function of eccentricity, dispersion in eccentricity as a function of initial eccentricity, it's actually remarkably flat. Right? On the other hand, the spread in inclination from ring-ring interactions, it increases very strongly as you increase the eccentricity. Right? So that means that then, thanks to Mr. Gauss, we expect the dispersion in inclination to be bigger, the heating rate in inclination to be bigger than the heating rate in eccentricity whenever the disk is eccentric enough, right? As long as the potential is close to eccentric. And of course, this is I only discovered this 2 weeks ago. If I'd read Royk and Tremaine more carefully, I would have realized, of course, this is just an example of the difference between vector versus scalar resonant relaxation, right? So the case here is that whenever you've got rings of stars precessing about one another, it's very easy to change the orientations of the rings, but it takes much longer time to change the shape of the rings, to change the eccentricity. Okay, so that's the first loose end taken care of. Right, the second loose end, well, it's a bit nastier. And that is that, well, if you look at some orbits in realistic disk plus potential, black hole plus eccentric disk models, you find that the Keplerian approximation isn't actually all that good, right? Just for some orbits. Right? This shows an example of an orbit that was initially basically close to circular in this realistic disk potential, and you see that it becomes, instead of having a nice, steady, almost circular ellipse form, it becomes a precessing ellipse, right? And the eccentricity of the ellipse varies quite a lot over periods of mega years, right? And it just becomes even worse whenever you add in pattern speed to this whole thing, because we believe the whole thing is probably precessing. Okay, so there's two ways you can approach this. One is you can try to model these orbits in the classical way as osculating stellar ellipses. That's what I would do, because I like classical mechanics, right? The alternative is, if you like computing, you say, life's too short, let's turn to Mr. Schwarzschild, right? So, just to remind you of what Schwarzschild's method is, he came up with this in 1979, right? And the motivation for this was that in 1979, in the 1970s, it was started to be understood that galaxies need not be axisymmetric. You know, they might look nice and regular and roughly axisymmetric, consistent with axisymmetry in the sky, but whenever you look at the internal, whenever you use the tensor virial theorem, there's actually no good reason why they have to be axisymmetric. Okay, so then the next nicest assumption you can make is that instead of having rotation symmetry about an axis, perhaps it's got reflection symmetry about three principal axes. In other words, perhaps it's triaxial, right? And then for a long time, people were wondering, well, not a very long time, for a year or two, people were asking the question, is it possible to have triaxial equilibria of stellar systems? And so the stumbling block there was that most people were used to thinking of this problem in terms of Jeans's theorem, right? And Jeans's theorem tells you that if you want to build an equilibrium galaxy model, then its phase-based distribution function must be a function only of the integrals of motion in that potential, right? But if you've got a triaxial potential, well, you only know one integral of motion, either the energy or the Jacobi integral. So how do you build a consistent model? And then in 1979, Schwarzschild pointed out, well, actually, you don't really care what the integrals of motion are. All you want is a model that's in equilibrium. We don't care what we label stellar orbits by. We just want them to be in equilibrium. So he completely turned this upside down and said, look, I just want an equilibrium. So give me a potential, give me a triaxial potential, give me your desired triaxial density distribution. Let's turn it into something the computer can do. So let's take this smooth three-dimensional density distribution, turn it into a three-dimensional histogram. So in other words, we discretize our density distribution. Then just follow a representative sample of orbits in your triaxial potential, right? Then for each, you probably know the story then, for each one of these orbits, you can calculate the contribution that that orbit makes to each one of your histogram bins. And then you've got a lovely, easy linear algebra problem to solve, right? And computers are extremely good at linear algebra, even though undergraduates aren't. So then in this method, then he demonstrated numerically that a triaxial equilibria do actually exist. Right? And this is now the most modern way of trying to get potentials in galaxies, the most general way. It was first extended by Ricks et al. In his modern form to estimate the dark matter distribution in NGC 2434. And then for most stellar dynamical black hole estimates, this variance in this are the method that are used. Okay. Here's an aside though. It turns out that Martin Schwarzschild was a very, very interesting character. I never met him, but I went to a conference in his honor one. So he worked on stellar structure, right? So he's one of the guys that's responsible for us understanding stars very well. And he pioneered the application of computers to solving the equations of stellar structure. Okay. And as part of his interest in stellar structure, he was one of the leading lights behind two telescopes called Stratoscope 1, Stratoscope 2. These were balloon-borne instruments, and they were intended for the study of the solar photosphere. Right? And so one of the things that was discovered from this was that convection in the solar photosphere is not, as was expected, nice and stationary before this. So basically, that was the motivation for doing this. But on the very, very last flight of Stratoscope 2 in 1971, they decided to point it at M31, right? And they saw that. So this was the first convincing discovery of the double nucleus in M31 from the Stratoscope telescope. That's compared to what it's like when we know from the WIFPIC camera and HST. Okay. And this paper, Light, Danielson, and Schwarzschild, 1974, they noted that this offset of the outer parts of the nucleus is puzzling. It's offset with respect to the main body of the galaxy. Okay. And the final interesting thing I want to tell you about Martin Schwarzschild was that after he retired, he decided that stellar structure, he didn't want to do any much hard work anymore, so he decided to turn to galaxy dynamics and develop Schwarzschild's method. Okay, so Callum, my student, he's applied Schwarzschild's method to this problem. Right. I'm going to sweep all the details under the carpet because there's an awful lot of work went into this, and there's a huge number of technical details that had to be overcome. Right. But so you can get a feeling for them. The problem here is the potential is now black hole plus disk, and in addition to the parameters we had before, we've got the black hole mass and three angles, plus we've got the mass of the disk the pattern speed of the disk and three-dimensional density distribution of the disk. Right? Okay, but Callum has done this heroic work. He's done this heroic scan over parameter space, right? And he finds here, this is what he gets for the different inclination angles. Oh, I should point out that the favored inclination here is 55 degrees versus 77 that we had before. My favorite black hole mass is, again, 10 to the 8 solar. And you don't actually get very strong constraints on the mass of the disk, but what you do get is strong constraints on the ratio of the pattern speed to the mass of the disk, right? Which is very tightly constrained in these. Okay, and another cool thing you can do about these models is, well, you can take the data, you make a guess for what the three-dimensional density distribution is to get the potential, then you work through the Schwarzschild modeling, and that gives you an updated estimate for what the density distribution should be in this model. And you can iterate this a few times until you get basically a model that's as self-consistent as you can make it. And I think this is the first time this has ever been done. And so the nice thing that we've discovered is that this iteration scheme, it improves the fit a bit, but more impressively, it actually seems to be stable. Right? You can do this and you can make your model more and more self-consistent if you like that kind of bookkeeping. You probably don't like that kind of bookkeeping. Okay, so here's a summary then of what Callum found. The inclination angle best fit is about 57 degrees versus 77 degrees for the main body. Right? We don't actually get very strong constraints on the disk mass and the black hole mass individually, but we know that the total mass, just essentially using the Virial theorem, it has to be about 10 to the 8 solar masses. We know the disk mass is less than about twice the black hole mass. The pattern speed, this is an interesting one, is less than 10 kilometers a second per parsec. It's also retrograde, right? And as I said, this ratio is not strongly constrained, right? And the distribution function is very similar to what we find in our naive Kepler models. Right? So that's all kind of boring, but there is one interesting thing here, and that's the fact that this pattern speed is so low. So for my last thing, this actually has some implications for P3. Right? So if you remember, P3 is this bright spot at the center of P2, right? So this is the V-band image of M31. There's P1, P2. P1's brighter in the V-band, but whenever you move to the U-band, it turns out that P2 becomes brighter. And that isn't really P2, it's really P3. Yeah. Okay, you can zoom in on P3. And this shows U-band image here before deconvolution. Then Todd Lauer and co-workers, they've deconvolved this. And you can just about resolve individual stars at the center. To give you a feeling for what that, you can also measure a density profile. Here it is. It looks broadly consistent with an exponential disk, because everything's an exponential disk, right? And the scale radius of this is about just under 1/10 of an arcsecond, right? Or about 0.3 parsecs. If you want to turn that into proper motions expected here, that's about 0.3 milliarcseconds a year. So we should be able to come back on this in a few years and see these points move if HST is still around. Right, the spectrum has been taken by Bender et al. And by Lauer et al. It's shown down here. My battery's down in this. It's shown here. And it turns out you can fit that very nicely by either using an A0 star or an SSP of around about 200 million years old. Right. And so everything about this, spectra, colors, the power spectrum of the surface brightness fluctuations suggests that P3 is a starburst that's around about 100 to 200 million years old. And there's actually a formation scenario for this, which I like because it's so simple and I can actually understand it. Right? This is put forward by Chang et al. And it's to do with closed orbits in this rotating potential. So the point is, this shows closed orbits in a model for this central potential that has a stellar mass to black hole mass of 0.1 and a relatively slowly precessing disk. The point you note here is that these orbits intersect at this radius, right? And so this led Chang et al. To come up with a nice simple model for how this might form. So in the old stellar disk made up of the P1 and P2 blobs, gas is being continually ejected from the old stars. That gas settles onto roughly closed orbits. Then the gas on these roughly closed orbits intersects at this point here, R2, and then some dirty physics happens, stars form, you get a starburst, and possibly you get young stars. I like it because it's simple. And the nice thing about this, or the interesting thing about this, is that it requires that the pattern speed of the disk precession be low. Right? Because here's a plot of the apocenter radius, right, versus pericenter radius of different orbits in this disk as a function of pattern speed. Right? So low pattern speed of 2 kilometers a second up to a high pattern speed of 9 kilometers a second parsec. Right? And what you find here, what you notice here, is that if the pattern speed's too high, then you don't get self-intersecting orbits. Right? So this nice, convenient explanation actually requires a low pattern speed. So I think that's something that's interesting for these dynamical models, because they lend credence to this model that I could understand as to how P3 might have formed. Okay. So, to summarize then, well, what we've done is we've looked at the structure of the second closest galactic nucleus, right? It's maybe not the most immediately interesting one is because we only see it in projection. But on the other hand, unlike the galactic nucleus in our Milky Way, we actually get a very clear view of the global structure of this particular nucleus. Right. This is one of the few galaxies for which we have very compelling evidence of a double nucleus. There are some other galaxies, like for instance, NGC 4486b, which is a companion of M87. It's just an extremely weird galaxy. It appears to have 2 almost identical nuclei in the center. It might also be explained by this kind of eccentric disk models. There are various other galaxies that might be explained by this, but they're all just basically too far away to tell. In this M31, we find that the black hole mass is roughly 10 to the 8 solar masses. We don't want to put error bars in that because we no longer trust error bars, right? And our models, I think they confirm the already compelling Tremaine 95 eccentric disk model for the old stars in this system. Right? So that basically, I think, explains the distinct old population, right? Except for P3, right? And this P3, of course, might be explained by the Chang model in this closed orbit argument. Right. One thing we haven't covered here is that this misalignment. So our favored disk model is aligned at has an inclination of 55 degrees, whereas the bulk of M31 is aligned at 77 degrees. We haven't touched on that. Okay. And the other thing I'm not going to mention is how did this form, right? There are various hand-wavy explanations for this. One relies on possibly, this misalignment suggests that you've got a triaxial bulge, right? Maybe that's a way of exciting an m=1 mode in this, right? Possibly it's just due to inflow, just causing a normal velocity Hopkins and Quatert explanation, or it could just be a natural counter-rotating instability in disks. Okay. There's some technical shortcomings that I haven't mentioned at all, right? I would feel guilty if I didn't get them off my chest now. So here they are. First is that we don't really understand the errors in the data, right? So often when people take, say, spectra, they're well-meaning and they will try to say, bulge subtract them. But then, we don't want them to do that. We want actual full spectra so we can do our own bulge model. And sometimes error bars get lost in the mist of time. So we don't want to push these models too hard. Right? Another very, very dirty secret on our part is that we think we've solved how to sample these Schwarzschild models in the horizontal direction very well. I think we've basically cleaned that one out. But when it comes to sampling them in 3 dimensions, that's not so good. And if I were to show you what one of these models look like when you see it face on, you might not believe me as much. But yeah. Okay. Then a more interesting problem, I think, here, just to end on this. Now, whenever we've done this, we've imposed this biaxial symmetry. So we've assumed that this disk has got two planes of reflection symmetry, right? We've just basically imposed that, and then we've used brute force numerical solution to try to find that equilibrium. Yeah. Okay. I think that's a reasonable first thing to do, but it's not the only possible solution for this disk in M31. You could well believe that given that it's embedded in this triaxial outer structure, possibly it should really be a warped processing disk. So maybe it's vibrating backwards and forwards, right? So it's not really steady in any one frame, but it always looks like a double nucleus. We haven't investigated that, right? And I think to really make progress in this, I think we're going to have to look at our own galactic center, right? Because at least in that case, in our own galactic center, you get 5 out of 6 of the phase-based coordinates, whereas in this case, we only get 3 out of the 6. So it breaks a lot of the degeneracy. So, okay, I'll stop there. Thank you.
Thank you, John, very much for this very nice and detailed overview of the dynamics in the center of the Andromeda Galaxy. The podium is open for discussions. Who would like to start? Andreas, just.
I have a question about the origin of this starburst. Is it possible that the M33, for example, is responsible when it was passing by?
Maybe. I don't have a good feeling for that. I think my suspicion is it's probably a bit too far away. But again, who knows what its orbit is? Really,
How close would you guess? Should it be 1 kilo or be closer?
yeah, it would make me slightly happier. Again, I don't really have a good feeling for how close it should be. In order to have an effect so far deep in the potential well, basically at parsec scales, I think we want something passing pretty close.
So you use this data to compare your model to, right? This is one-dimensional slit data. How much better could you do if you had integral field unit data? And like in terms of getting the uncertainties of the black hole mass, for example, and also the disk mass. I think there, if you could get further out and get a clearer picture of the disk dynamics, maybe you could improve on that.
Yes, absolutely. But I think I agree with you. We're already we're not in the. What I showed you, we post hoc predicted Oasis integral field unit data, and it seems to fit very nicely. Of course, it's not as high resolution as this. And then since then, Callum in his thesis, he's also fit the Oasis integral field data. And again, it basically doesn't change the model assumption very much. But I think what you really mean if we had really, really high, if we had a muse in the northern hemisphere and we could probe everything, then I think it would be fantastic. But the danger there would be, I think we're already hitting the systematic errors in the model. So, to be honest, I probably shouldn't say this, but no, I should say, no, yeah, we need much better data so we can really rule out the model. Yes.
So, Jessica Liu, she has beautiful NIFS data. Jessica Liu.
Okay,
You should talk to her. She has beautiful NIFS data that cover a larger field of view than this.
It's higher resolution.
It's adaptive optics in the near infrared, yes.
So next question from Finland.
Okay, so that was also one of my questions. There was a lot about the modeling, but one question about this P3. Maybe that's an aside, but if it has formed from this accumulated gas from old stars, if I understood right, at this pericenter region, this gas, if there's a net rotation, should still have angular momentum, plus this this gas probably hasn't only appeared at one particular time if it's from old stars. So is this an accepted hypothesis, or I would think, like, first of all, that cluster, if it had formed at a short time, would still rotate and just coincidentally be at the position where it's now, or a ring should have formed maybe. So I was just going to get your thoughts on that.
My thoughts are that, yes, I just treat this as a very simple initial guess scenario, but I think it needs to be investigated more. So, I mean, it might be worth, it could well be that China have answered the particular question you're addressing about, should this be a ring, should it really fall towards the center? But to my memory, it's been a long time since I looked at this, as far as I can remember, they don't.
But it's for sure not around black hole. Right. Or, so that's right. Black hole's not there, right?
Black hole in P1?
No, the black hole's in P1, so the black hole in this case would be here.
Where's P2?
There's a right there. Yeah, P3 is right more or less on the black hole. Yeah, so this, right, so the gas all binds up together here, and it has to travel this distance, and it has to fall that distance in the potential well. And exactly how it does that, I think, is just hand waving. Yeah. But I would recommend going back to the original paper just to check that I'm not, having missed something.
While I make my way to Sasha, let me follow up on the question. I mean, these stars seem to be young because they're bright and blue and so on. And he would say if this is a continuous process, gas is continuously coming, it should be a ring. So couldn't it be some, like in the galactic center, accretion from further out that happens to sit there and does its star formation dance?
Yeah, could be. But personally, what I like about this is that I kind of wonder, it's clean, and it just, well, it's not that clean, but it justifies our low pattern speed.
But do we know something about the ages of the old stars? Maybe there is a particular burst of, winds they let loose, and this could lead to this, excess of star formation there?
Yeah, there's nothing unusual, but they just seem to be very, very, very old.
Okay. So
I think this scenario, shouldn't it also predict a relatively peculiar abundance pattern of those stars? Because the gas that's lost from old stars has a very peculiar self-enrichment pattern. So is there anything, because you did show some spectroscopy, so is there any indication that these stars are strange in their abundance patterns?
Can you tell?
I can't, but maybe, is there any mention of this in the literature? Because so the old stars, they are carbon, nitrogen, and oxygen enhanced very strongly compared to the normal ISM.
I don't know the answer to that.
Okay.
Yeah, there might well be signs there, but it wasn't really my primary interest.
Okay.
So again, the original spectrum was taken in this paper by Bender et al. 2005, and then another paper reads Magorrian et al. 2015 when they do the photometric analysis. But as to actual details of one of them, I'm not sure.
So Matthias Amani?
So what about the vertical structure of this disk? Why is it so disky and is not a spheroid, for example?
Because angular momentum. Well, of course, angular momentum is not actually conserved in this case, right? But there are. You're basically asking how did it form?
Yes.
Okay. Well, okay. One scenario is that it is. You start off with an initially axisymmetric disk onto which you dribble something on a counter-rotating orbit. And then that naturally undergoes an instability, and it does heat both eccentricity and inclination, and it does leave you with a disk behind rather than a spheroid. And you start with a disk slightly perturbed with some counter-rotating stars, and you get a different sort of disk that is spheroid. That's just one possible duration scenario.
It was deeply, right?
Oh, tilted with respect to the main body.
Yes.
Yeah, again, who knows? Triaxial bulge, who knows? Could be being driven. I mean, one of the explanations for the work in the young stars at the galactic center is that they are being torqued by not just the black hole, but the older stars around them. So that causes this natural misalignment. So there are various ways you could get a misalignment in this disk, but to be honest, they haven't been investigated that thoroughly yet.
So I see no more hands up. With that, let us thank John again for this very nice talk.